Hi folks! So today we're going to go through Lab 4, the Regression Summary Lab, which is a Quarto document, and you can download it from Canvas and put it into your folder for this class. I'll open it up here, and the first thing that I usually do is hide my document outline so I have a little more space right there, and maybe I'll smoosh this over a little so I can see it better. We're going to start with loading a couple packages, and then we're going to get some data going. So I have the fuel economy package installed on my computer. If you don't, you might need to put that install.packages fuel economy in your console and hit enter. I'm not going to do that right now. And then I'm going to hit the play button to load that data in. Probably can't see it in my environment, but it's loaded in as a promise. And I could skim the data to get a little bit of initial information about it. So to see the kinds of variables that I have and the summary statistics of them. So this has a few character variables. Those are kind of like categoricals, like the make, the model of the car. It's got some numeric variables like the year of the car, the number of cylinders, the displacement, the highway and city mileage, things like that. And we can see, for example, the mean, the average year that these cars were released was 1999. The P0, that's the smallest number, 1984. P100, that's the biggest one, 2015. So we've got data about cars. And for this lab, I only want to think about vehicles that were released in 2000 and have 4-cylinder engines. And so I'm going to make a little subset of my data just with those cars. And the way I'm going to do that is I'm going to filter my data. I'm going to give this filtered data, it's going to be smaller than my original data. I'm going to give it a new name. So my vehicles data right now, if you can see in your environment, has 33,442 observations. And when I click the play button on this chunk of code, I'm going to get a new thing in my environment called my cars. And I know it's going to have fewer observations than my original data set. And I'm filtering that the year is equal to 2000 and the cylinders are equal to 4. And I'm using the double equal sign to mean we're going to check if it's equal. So if I wanted to say I want it not equal to 2000, I would use the exclamation point equal. I could use the greater than sign to mean greater than. I could do greater than and then an equal sign to mean greater than or equal to. But I'm just doing exactly equal to 2000 and cylinder equal to 4. So I click play on this. And now I have a new data set. It's in my environment. It says 296 observations of 12 variables. I'll click on it so I can see it. So all the years are 2000. When I go over, all the cylinders are 4. And I could skim again to kind of look at my, my smaller data set. So this data set, the mean year is 2000, the minimum is 2000, the maximum is 2000 because we filtered it, but I could see the statistics for the other variables. So the first thing that I want to do is think about a relationship between two variables in this data set. Let's think about the relationship between the displacement of the engine, that's kind of how big the engine is, and the highway mileage that the car gets. So I'm going to do a ggplot. My data is my cars, and then my x is displacement, y is highway. I'm putting alpha equal to 0.5 so that my points are a little bit transparent. So I'm going to hit the play button here. Maybe I'll smoosh this over a little bit. So I can see that there are some places where it's kind of light. Maybe there's only one car that has a 2-liter displacement and, about 34 miles per gallon. But some of these are really dark because there's a lot of cars that have those qualities. And I could drop down that alpha even more to make them more transparent. Probably this is too much because now I'm starting to not be able to see some of the points. Let's put it back up a little bit. But overall, it looks like there's kind of a linear pattern. It's a negative pattern. And so maybe we can choose to fit a linear model. So I'm going to use my dumb naming convention. I'm going to call my model M1. I'm going to try and predict the highway mileage based on the displacement. And I'm going to hit Control Enter or Command Return to just run one line of code at a time. So I ran that first line of M1. Now I've got a model in my environment. And then I could Command Return to get a summary. So I can look at this summary. Then there's a new thing, which I don't think I've shown you before, which is the ANOVA command, which will show me an ANOVA table of a model. So I'm going to Command Return on that and show you this. So let's look at these outputs. So when I look at the summary of a model, I get things like the estimate for the intercept and the estimate for the slope. I get p-values, which we're going to talk about. I get things like the r-squared value. When I run the ANOVA, I get an analysis of variance table. And so this has a row for my variable, but it doesn't give me the estimate. So I couldn't write out the equation of the line from this information. It does give me a p-value, and that p-value kind of looks the same as up here, but it's basically 0, less than 2 times 10 to the negative 16th. But it gives me information about the degrees of freedom, the sums of squares, things like that. So it's just different information about the model. So if we were going to do inference about this model, there's a few things that we might want to do. We might want to think about p-values. We might want to think about confidence intervals. Those are ways that we could assess our model. Another way that we could assess our model is we could compute the r-squared value to see what proportion of variability in the response can be explained using the explanatory variable. So if we look at the summary table of the model, it tells us the r-squared right here. It says it's 0.3061. And so sometimes a homework problem will just say, like fit a model and then, tell me what the r-squared value is, and you could just read it right off of here. But sometimes the homework problem is going to say, you need to compute the r-squared yourself, and maybe you'll get an ANOVA table like this. So you'll get something about the sums of squares, and you'll have to compute the r-squared value yourself. So there's a couple of equations for the way to find r-squared. Maybe I'll write them out here. So either you could do the sum of squares of the model over the sum of squares total, or you could do 1 minus the sum of squares of the error over the sum of squares total. And we're given some sums of squares here in the ANOVA table. So if I had this ANOVA table and I wanted to find the r-squared value, I could either take the SSM and put it over the SST, or I could take the SSE, that's the sum of squares of the residuals, divide that by the SST and subtract that all from 1. The thing that isn't given in the ANOVA table is the SST, the total sum of squares. But what that is the sum of squares of the model, which in my case is 1714, plus the sum of squares of the residuals, which in my case is 3,885.7. And so my total sum of squares is 5,599.8. So I'm going to do the sum of squares of the model, that's 1714, over the sum of squares total. And I guess I could just hit play on this code chunk, and I get that exact same number that we had in the summary table, the 0.3061. So what percent of variability is explained? The model, using displacement as a predictor, explains 30.6% of the variability in highway mileage. So is that a good r-squared? Is it a bad r-squared? It really depends on the context. I think that it's probably decent for this case to have 30% of the variability in highway mileage explained by displacement. So that's how we would find the r-squared. So now let's go on to our inferential tasks. First inferential task would be doing a hypothesis test. And when we're doing linear regression, our hypotheses are always beta 1 equals 0 and beta 1 not equal 0. So we're always doing that two-sided hypothesis test. And then if we want to make a conclusion about the hypothesis test, we need a p-value. So there's two ways to find the p-value. One would be if you're allowed to make the model like this, you could just literally look in the table and say like, yep, that looks really significant. The p-value is basically 0. It has 3 stars. That means it's really significant. So I'm going to reject the null hypothesis in favor of the alternative. But sometimes, like on an exam, you're only given part of the information. So for example, on an exam, I might black out the t-value for a particular coefficient and the p-value, and you would have to compute that p-value by hand. So let's pretend like we don't know that p-value. So the way that we find a p-value is, first of all, we find a test statistic. And for doing the test for a slope, the test statistic is going to be the estimate over the standard error. And I'm never going to ask you to compute the standard error by hand. I'm always going to give it to you. So in this case, my estimate is negative 8.3, and my standard error is 0.7289. So my test statistic that I'm going to compare to a distribution is negative 11.38. So our test statistic is negative 11.38 or 39, maybe if we want to round. And so now we want to find the p-value. And what that means is we need to compare that test statistic and see how extreme it is in the context of a distribution. And in linear regression, we're going to use the t-distribution as our reference distribution. You can't memorize things about the t-distribution, but I have a few facts memorized about the normal distribution, and I know that the t-distribution converges to the normal distribution eventually. So one of the facts that I have memorized about the normal distribution is that if a test statistic is more than 1.96 plus or minus 1.96, it's going to be significant. And so is negative 11.39 more extreme than plus or minus 1.96? Yes, it is way out in the tails. So if we were doing this with the normal distribution, we'd expect to see a significant p-value. So I'm kind of expecting that with my t-distribution. And the way to find the p-value, well, you could use a table. I'm not big into tables, so we're going to do it with R. And to do this in R, we're going to use the PT function, which is the student's t-distribution, and it's going to give us the p-value for a t-distribution. For the PT function, you have to put in the test statistic, like negative 11.39, and then you need to put in your degrees of freedom. And the degrees of freedom for linear regression are n minus k minus 1, which in this case is n minus 1 minus 1, so n minus 2. And what was my n? You probably can't see it in my environment, but I have 296 observations, 296, and then minus 2, and I'll just let R do the math for me. And if I hit enter, I get this p-value of 1.9 times 10 to the negative 25th. That's for one side of the distribution, and we're always doing a two-sided test in this class, so we need to multiply by 2, and that's what I'm doing here. So here's my actual p-value. It's 3.852847 times 10 to the negative 25th. It's not exactly the same as what came up here, but it's basically saying the same thing. It's 0. The only tricky thing is if our test statistic had been positive, like if we had found positive 11.39 and we had tried to do this, it would have given us a p-value of 1. And that's because R always finds the area of the distribution that is to the left of the test statistic. So if you have a positive test statistic, it is going to give you this whole big area. Let me see if I can give you a little visual reminder of that with a package that I don't have loaded. Let's see if I can do it. So here's a t-distribution. I'm going to use a less extreme test statistic. Maybe I'll do like 2.4. So if my test statistic was positive 2.4, you can see the line between the green part of the distribution and the purple part of the distribution. And what I'm interested in is the green part. That's the little tail. But what R is giving me is that whole purple area, which is the big part of the distribution. So there's two ways to deal with this. One way would be to do 1 minus that number. So, you've got the area that's to the left and you really want the area to the right. You could do 1 minus. The other approach would be to put in lower dot tail equal false. So when you put in lower dot tail equal false, that means don't do the lower tail, the left tail, do the upper tail. And so then that would give you the appropriate p-value. So you kind of have to think about which end of the distribution is your test statistic on, what direction is R going to be thinking about, and how does that all work together. Okay, our next inferential task would be to find a confidence interval for the slope. And if I was being nice, I would let you use, fit a model and then use confint. That's the function which will make a confidence interval for you. So if I do confint M1 and hit enter, it gives me a 95% confidence interval by default. The columns are labeled 2.5% and 97.5% because those are the little tails out there. So I want 2.5% more extreme on one side. And then again, because R always counts everything to the left, I want 97.5% to the left because that's 95% plus 2.5%. So this is by default a 95% interval, and I will do the interpretation sentence. We are 95% confident that for a what are the units in displacement? I think it's liters. A 1 liter increase in displacement, the highway mileage of a car changes between negative 9.74, let's round, and negative 6.87 miles per gallon. So basically, as the car gets heavier, we expect the highway mileage to go down between 7 miles per gallon and 10 miles per gallon. So that's that negative relationship. Let me scroll back to my plots. So the slope value from my summary was negative 0.8. So if I was going to write my sentence for that slope, I would say for a 1 liter increase in displacement, we would expect the mileage to go down by 8 miles per gallon. But we might want to make this inferential task and have that confidence interval. So that interval is all negative. That means we're pretty confident that there's actually a relationship. So when we looked at our p-value, it was really small and we were able to reject our null hypothesis. Now we've made a confidence interval and that is all negative. It doesn't contain 0, so we're pretty confident that it's negative. But sometimes I'm not as nice, the book's not as nice, the world is not as nice as to let you make the model and then use the confint function. So there's also a way to find the confidence interval for the slope by hand. And the way that we do this is always our point estimate plus or minus something that depends on the distribution times the standard error. I've already said I'm not going to make you compute the standard error by hand. So I'm going to give you the beta 1 hat number and the standard error number, but you're going to need to find the t star number. So my point estimate, that's my fitted beta 1 hat, is the negative 8.3. My standard error is the 0.7289. What's my t star value? Well, again, I could use a table, but in R, we're going to use the qt function. So that's also about the t distribution, but it's going to find the quantiles. And for this one, we're going to put in 0.975. And again, we need to tell it the degrees of freedom, 296 minus 2. If I do this, it'll give me a critical value. Why the 0.975? Again, it's because 0.95 plus 0.02 5. We want the area such that there's 2.5% on either end, and that means that we want the area where 95% plus 2.5% is more extreme, so that's 97.5%. So my critical t-value is 1.968. That's very similar to the critical z-value that I have memorized about the normal distribution. It's a little bit different, 1.97-ish, but that's kind of what I would expect. So I could put that into my, my confidence interval. Oh, what if I needed it for a 90% confidence interval? I could, copy this same information, and I'd have to think, okay, 90% in the middle. That means 5% on either side. So it's 90% plus 5%. So I'd put in 0.95, and that would give me the critical value for a 90% interval. But in this case, I'm going to make a 95% interval. I'm going to use that 1.97. So I've got my point estimate, my critical value, my standard error. I've got one with a minus and one with a plus. So I got negative 9.73 and negative 6.86. And that's the same interval that we found using the confint function. So it's going to come out the same whether you do it by hand or you do it using the confint function. That's another inferential task. All right. What's something else that I might make you do? Maybe I wouldn't be so nice as to give you the value for your beta hats, for your beta 1 hat and beta 0 hat. So if that was the case, we have a formula to compute the slope of the regression line using the correlation between the response and the explanatory variable, and then the standard deviations of the response and the explanatory variable. So here's my equation, and I could look at the skim to remember those summary statistics. So let's see, I'm going to smoosh this out so it looks a little nicer. Let's see, so the standard deviation of my y variable is highway. So here's my row for that, and the standard deviation, 4.36. And my x variable is displacement. So here's displacement, and my standard deviation is 0.290. Okay, so I've got my stuff for this fraction. Then I need the correlation, and here's one way to find the correlation. Do my cars, and then summarize the correlation between those two variables. They're negatively correlated. That's kind of what we would expect, negative 0.553. And now I've got everything I need to use that equation. So let's use R as a calculator. I'm going to put in this correlation times, and then I need to find my standard deviation for y. Again, y was highway, so that was the 4.36. And that's going to be divided by the standard deviation for x, which was the 0.290. And now I could hit the play button. Negative 8.31. Was that the same one that we found? Negative 8.3. Yeah, it's basically the same. There's probably a little bit of rounding that was different. Okay, so now we've got the slope. What if we need to find the intercept? So one thing we could do is use the point slope formula for a line. And the way that we use this is we plug in y bar and x bar. The point x bar, y bar always is on the regression line. Like that regression line is always going to go through the mean of x and y every single time. So if I wanted to find beta 0 hat, I could put in y bar minus beta 1 hat times x bar. And again, if I look at that skim, let me hit the up arrow a couple times, I can find those x bar and y bar. Those are the means. So let's see, y bar would be highway bar. That's this mean. Minus my beta 1 that I had just found, which was this. It's going to be like minus a negative, so maybe I'll put it in parentheses. Times, and now I need my x bar. That would be my displacement bar, which is this mean. Hit the play. Okay, 44.46. Is that what we had found? 44.37. Yep, pretty close. I think it's just based on rounding. So if I wanted to write out my equation, I could say highway hat is equal to 44.46 minus 8.31 times dispel. That would be my equation, and it's basically the same one we got from the summary. Okay, I've got two more things to talk to you about. So there's prediction intervals and there's confidence intervals. And this is one of those things statisticians should not have been allowed to name because we have the confidence interval for the slope that we talked about before. And then we have these intervals that are for a specific value of x, either for the mean of y for a specific value of x, or for a particular y for a specific value of x. So either way, if we're going to make a prediction interval or a confidence interval for a specific x value, we're going to use the predict function. So here's how it works. I do predict, and then I give it the name of my model, in this case M1, and then I have to do some new data. And what my new data is a data.frame, which is a tiny little mini data set. So if I paste that in here, it's a data set. It has one observation and one variable. The variable is displacement, and the one value is the one that I'm interested in this case. So we're going to try and figure out if the displacement was 2.4, what would we think would be our average highway mile per gallon? We have to put in that as a new data frame. And then we have to specify whether we want a confidence interval or a prediction interval. So I'm going to hit the play button here. And it gives me the fit. That's the predicted value, the point estimate. And then it gives me the lower value and the upper value. So this is actually my confidence interval. That fitted value, that's what I would have gotten if I would have plugged into my equation. There's my intercept, and there's my slope, and then let's multiply by 2.4. That's my point estimate, my single best estimate. But if I wanted to make an interval for a mean, this is the one. So here's how the sentence goes. We're 95% confident that the mean fuel economy for cars with a 2.4 liter displacement is going to be between the lower end of that interval and the upper end of that interval, 23.78 and 25.12 miles per gallon. Then, if we wanted to do a prediction interval, we would do the exact same code. The only thing that's different, instead of interval equal confidence, we're going to put interval equal prediction. If I hit play, again, the fit, the point estimate, is always going to stay the same, but the interval is going to be different. And the prediction interval is always wider than the confidence interval. So this one was like 2 miles per gallon wide, and this one is like, 15 miles per gallon wide. It's much wider. And if I want to interpret that, I can say, we're 95% confident that the fuel economy for a particular car with a 2.4 liter engine displacement is between 17.26 and 13.64 miles per gallon. And last lab, we talked about putting a geom smooth onto a scatter plot, and I was doing SE equal false to not have that standard error bar. Now, if I put in SE equal true, I can see that standard error, which is the confidence interval over the whole model. And it's maybe a little bit hard to see here, but this interval is going to get the narrowest right near the mean of displacement. So it's always going to be right in the at the mean is going to get the narrowest. And if you look at the formulas for the standard error, you can kind of see why that is. I talk about that in the lecture videos. But I'm not going to ask you to compute those standard errors by hand. You would always either have R and you'd get to use the predict function, or sometimes on an exam I'll give you the output and ask you to interpret it. Okay, I've got one final thing for the problem set, it's like a little more intuition about transformations. So I have this model. I could look at the LINE conditions. I could look either at the which equal 1, let's run that. That's the residual versus fitted plot. Or I could look at the which equal 2, that's the QQ plot. And residual versus fitted plot, that red line looks pretty flat to me. I think it looks pretty linear. I don't see like a super intense fan shape. It's not like the best equality of variance, but it's not terrible. But when I look at this QQ plot, that looks very not normal to me. And so I'm a statistician. I'm going to just try doing some log transformations. So if I hit play, now I've got more variables in the my cars data set. I have 14 variables. I could go look, scroll over. Got my logged displacement and my logged highway. And I could make a model with that. So I'm going to call it M2. So we can use this model basically the same way we do with an untransformed model. So we could try to make a prediction, but we can't just plug in dispel equal 2.4 anymore because our model is going to expect the log of dispel. So if I plug this in, it says error in eval predvars, object transformed dispel not found. And that's because the model is expecting the log. So we need to give the predict function the variable name that it expects, which is transformed dispel, and I need to plug in the value in the correct scale. So if I put in 2.4, that wouldn't be the right thing to plug in. I need to put in the log of 2.4 in order for that to work. Now it's going to run, but my fitted value isn't in miles per gallon anymore. It's in the log of miles per gallon. So remember when we plugged in 2.4 before, we were getting a predicted value of like 24.45 miles per gallon. 3.19, that's not a sort of reasonable mileage for a car. So that's our indication that maybe we're not in the regular scale of the data. So if I want to interpret this, I probably want to transform back to the original scale of the data. So, I mean, I could write it. I'm 95% confident that the log fuel economy of a particular car with a 2.4 liter engine is between 2.94 and 3.45 log miles per gallon. But it's easier for me to think about it if I convert back. So one thing I could do is I could use the exp function. That's to exponentiate a number. So if I exponentiate this 3.19, I get something pretty similar to my previous predicted value. So I could use R like a calculator. I could, do that for the lower end of the interval and the upper end of the interval to get the ends of my interval. Or I could exponentiate the whole thing. So I could wrap exp around my predict thing, and then everything that comes out will be exponentiated. So it exponentiates my fit, it exponentiates the lower, it exponentiates the upper, and now we're back in miles per gallon. And so we can say, I'm 95% confident that the fuel economy of a particular car with a 2.4 liter engine is between these two different numbers. It's a little bit different interval from before because we did those transformations. So that makes much more sense in the scale of the data.